const it onto the rest of recursing, the result of recursing on the rest, or filter selectively const it onto the rest, but without actually looking at the rest. So anytime you're actually going to use, or the already, without actually looking at the already recursed on rest. So anytime that you're looking at the current first and actually using the result of the already recursed on rest, that's when fold is a good candidate. If you're just using the first one and then doing nothing more to the result of the rest other than just consting onto it, you might want to look at map or filter. Okay. So map again is going to apply a function one by one. Every element of the list to give you a result that's just as long. Filter will apply a test, a predicate, that returns true, false, and it will only give you a list of the results that pass of the elements of the list that pass that test. And then fold again is going to receive, your operator is always going to receive two parameters, and so the key is designing that operator. Once you have the first, if you go back to your previous lab and look at how you coded it, if you coded it well, recursively, there's probably a point for the ones that you'd be using fold where you're doing something to the first item in the list and the already recursed on rest. And so package up that something as a function, and that's what you'll use for fold. Any questions about that lab? How many have completed already, just out of curiosity? Okay, so some already. Good, good. The rest of you aren't expected to. That was just to help gauge. For the next one, you're going to be building a couple of decorators. And so towards the end of class last time, I showed you this idea of using a function that kind of creates a new function that has a wrapped around layer of functionality around some other function. We talked about that key idea last time, but there's actually some racket nuts and bolts that we need to spend about 5 minutes on today. And so I wanted to just show you that. The example I gave you, and I'm not going to code the whole thing, but the idea was that, so I did something like this, and then we did a function that sort of wraps a layer of functionality around it. So I'm not going to do the full version, but I'm just going to go ahead and do just a little bit just to okay, so I'm not even working about putting in a label or anything else just like that. But at the heart, actually, so let me go ahead and just actually sorry, I goofed. Remember, the idea is it's making and returning a function that that receives a parameter. All right, sorry. So remember, the basic idea was these decorators take a function in, return a function back. When that function is called, at the very heart of it, it simply calls this function that was first passed in. Okay? So it's simply calling this one with whatever parameter is passed when this decorated wrapped around function is called. And then that now gives you the ability to stick a little bit more in there. So notice if we took out this line, we'd have nothing. It would just simply do nothing but call this function. So that was the simple make copy example I had last time. Before I move on, let me just use this as an opportunity. We didn't have a lot of time to talk more about this or to ask questions at the end last time. So any questions about this? Do you get the basic idea? All right. Now, this works fine for a one parameter function. But for some of the, well, for the things you're going to need to do for the programming assignment for the lab, you actually need to do this for multiple parameter functions. So let me show you how to do multiple parameter functions in Racket. So the way that we've been writing functions here, and I'm going to write it with the lambda notation. So I could write a function add all that takes, say, 2 parameters and adds them together. Or I could extend this and make it 3, but you'll notice all of these have so I could do it with 2 parameters, I could do it with 3 parameters, I could do 4 parameters, but all of those are fixed arity. We haven't talked about how to do variable arity functions. Sorry, does everybody know what I mean by variable arity? Functions that, remember, the arity of a function is the number of parameters it takes. Variable arity functions take an arbitrary number of parameters. And so, or sometimes it's n or more parameters. The way that you write a fixed arity function is what you've been doing all along with Racket. You actually provide a list here of each of the 3 or 4 or 5 or however many parameters you have. To write a variable arity function, instead of putting each formal parameter in a list this way, you just give it a single parameter, not in parens. So instead of a list of the names of the formal parameters, you give it the name of a variable that will receive a list of all of the parameters that are passed. So I usually just like to call this args, but you can call it whatever else you want to. There's nothing magical about a keyword args. The keyword is there's no paren around the name. So now what happens is this will, if I call add all, it will take all the parameters that are passed, wrap them in a list, bind them to this variable args, and then I can just process that. So if you're used to variable arity parameter passing in C, or even command line parameter passing in C or C++, this is roughly the equivalent of argc and argv. Okay? It's just that it's a list, not a vector, so you don't need argc. Just if you want to know how many parameters were passed, just ask for the length of that list, and then you just access them like you would any other list. Okay? Now, if I run this, we're going to get an error. Like, can everybody, well, sorry, let's just change. All right, of course, I couldn't find the XYZ, but now if I do plus args, what's the error? Yeah.
You're passing a list instead
Right.
of...
Exactly. I'm passing a list to plus, and it doesn't know what to do with that. Now, I could go ahead and write some other version that adds things up or does a sum of a list or something like that. But there's another operator, and it's called apply. Some of you have seen it before and asked me about it. I think you were asking about it last time. What apply does is apply takes a function with some number of, that expects some number of parameters, and a list, and calls this function and passes it each of the elements of this list as the 1 by 1 by 1 parameters. Does that make sense? So here in this case, apply plus to the args list is exactly the same as under the hood calling plus with 3, 4, 5.
So you're saying it's not recursive, it spreads out the list and passes it all at once?
Passes it all at once, yeah. So it doesn't recurse on it, there's no folding or anything else. It just, so think of it as one call with n parameters. So I often like to differentiate between this and map. So map takes a 1 parameter function and makes n calls, 1 for each element of the list. Apply takes a function of arity n, or variable, makes 1 call, passing all n parameters at once. Does that make sense? So you see the idea of how to do variable arity functions? and
So-
use them with apply?
So if apply is not recursive, how
Right.
do they do that?
Think of it as actually just under the hood, pulling out the elements of the list and passing them as the parameters to that one function call.
Okay, so it's an implementation of the language itself
Yeah.
rather than.
Right. This is sort of built into the language.
Okay.
So under the hood, it's basically making one call to plus with 3 parameters. Or one call to plus with 5 parameters. Does that make sense? So if this is a fixed arity operator, you better pass it a list that has the correct length. If it's a variable arity operator, you can pass it a list of any length. Now, you don't have to use apply when you're doing variable arity functions. You could do all kinds of other things. You could just process the list yourself. But for these decorators, it's a useful combination. So going back to this other example, if I wanted to add a debuggable version for functions of any arbitrary arity, not just, again, this one works fine for one single parameter function. What I can do is instead of giving a single parameter x, I'll make the function that's returned, the decorated one, variable arity, and instead of calling that function with one parameter, I'll apply it to the list of parameters. Okay. Where did I? Oh, I'm sorry. That actually was the earlier. You guys may have done that as well, sticking in an extra set of parens. That's when my C programmer brain starts kicking in for the syntax. All right, so notice it works fine for a one parameter function, but I could do something like, I could wrap this around some other thing that is, well, I could even do something like define so I could debug every call to the plus operator, just as an example. And so you see how I can work with one parameter, but I can also decorate something of any arbitrary arity. Does that make sense? So if you actually look at the notes that I distributed for last time, the cleaned up examples, there are 2 other examples, both of which use this idea. And actually, I think I specifically developed this idea with the debugging one in those notes. So I just wanted to take a few minutes in class, but not a huge amount of time. Questions about this? Okay. All right, so go back to our schedule. We are now going to switch topics. So we've been talking about, so we talked about some basics early on. We've been talking about a different kind of a programming paradigm with functional programming. We're going to come back to that a little bit later when we're going to use another functional language that also brings in another kind of a twist to it later on called Haskell. But for now, we're going to wrap up Racket. So we're kind of entering that phase where you've seen this before in some classes, where we finished covering one topic, but you're still doing the labs for it, while we're now starting on some new topic that sets the base for your next lab. So we're now going to start actually building interpreters. So we're going to see what happens under the hood. We're going to look at the nuts and bolts under the hood of some fairly simple interpreters, but we're going to talk about the core pattern that underlies just about all tools that work with code. Okay. Interpreters, compilers, JavaDoc, all kinds of things like that, all actually have the same internal structure. That's what we're going to talk about next time. We need to first sort of take a slight detour. We're going to write these interpreters in a language called Julia. Okay. How many of you have ever used Julia before? Okay, that's about what I expected. It's a somewhat newish language. It's been in development for about 10 years, which might not sound new, but for many languages it takes a while to sort of evolve and develop, and eventually, actually just over the summer, the Java developers, the Julia developers just officially took it 1.0. So it's the real full release, not just development version. In the process, so what happens is as a language is developing, they may sometimes change some things because you're sort of figuring out what works, what doesn't when you sort of put it out there in the wild. All the versions up to 1.0, whenever they would change something that broke backwards compatibility, they would keep that around but give you a little warning that that feature was deprecated. Once they went 1.0, they said, all right, fine, we've given you enough warnings. If you haven't updated your code yet to sort of the current version, you need to now. So if you go and start downloading the versions of labs, the code that we distribute for labs right now, it won't actually work. I've got cleaned up versions that I need to post. And so I've actually been working, or took some time over the summer, revamping some of our code to make sure that it works with the latest version. So just giving you a bit of a heads up. Some of the code that was distributed for previous semesters, well, not just may break, will break at some key points, just based on some changes that they've made. So, but the nice thing is it's 1.0 and it should be fairly stable for a while. So Julia, its background is originated out of MIT. How many of you have ever programmed in Python? Okay, so a lot of you. Julia is going to look a lot like Python in terms of a lot of its aspects. But the problem is Python is really slow unless you learn to use vectorized operations. You guys have probably seen that already. With Python, if you're using built-in vectorized operations, it's really fast because it's calling compiled code. If you're writing your own for loops, it can become super slow. Julia tries to avoid that. It's actually compiled. It aims for the same kind of target audience that Python would be used for, at least the way Python is used in data science, high-performance computing. I know saying Python and high-performance computing in the same sentence probably is an oxymoron, but it's used a lot for deep learning and other kinds of things like that. So Julia aims to sort of fill this niche of a really high-performance language by being compiled. But it actually does a really cool thing where it looks interpreted, but it basically, as it interprets your code, it compiles it and caches it and reuses it. That's in essence what, if you've ever heard of just-in-time compilation, that's actually what that's also doing. It's the same idea. And so Julia can actually have some pretty high performance. It also has a lot of other nice features. One of the nice things is when you start from scratch with the language, you're not burdened by a lot of stuff backwards compatibility-wise. You get to borrow and beg, steal everything from all the best of other languages. So you'll notice as languages evolve, languages will steal from each other all the time, right? C++ actually stole a lot, not just from C, its core, but from a lot of other languages, a lot of concepts. Java stole a lot of other concepts. Julia does as well. So Julia actually turns out to be a pretty good language for building our interpreter. And so we're going to build the interpreters in Julia. One of the things that we're going to talk about more next time is this idea that an interpreter is working on a particular target language, right? So for example, Python is interpreted. So if you have a Python interpreter, its target language, the one it's interpreting, is Python. What's the Python interpreter itself written in? Yeah, some are written in Java, some might be written in C++. As a Python programmer, do you care? Right, you shouldn't. Right? If you ever have to, that's really bad. So again, we'll come back and we're going to talk about this idea a couple of times as we start writing our own interpreters. So the implementation language, the language we're going to use to write the interpreters, is Julia. The target language for our interpreters as we start building them is going to look like a little subset that's very Lispish. Okay? Mainly because it has a dead simple syntax, as you've already seen. All right, so let's dive into Julia. So, actually, let me back up here. So if you go to julialang.org, that is the home for Julia. You can go right here to download 1.0, and that will let you download a version of the language for your whatever platform you're using. So you can use, it's got binaries for Windows, for Mac, for Linux, and so on. Okay. All right, all you Linux users, if you really want to download source and build, you can. But everybody else, use and even the Linux users, I would recommend using the binaries. So you can download this. There is also a really useful set of tools called Juno. Whoops. It's not.
Juno's still a thing, huh?
Pardon?
Juno Internet is still a thing.
Yeah, I know. I'm just making sure I get the right. Let me just actually do a search this way. Oh, sorry, junolab.org. All right, so I'm going to be demonstrating it using an IDE that's called Juno. Juno is really a set of Julia bindings and plugins for an editor called Atom. So when you see me running things, I'm going to be running Atom with Juno add-ins that create a Julia-style IDE. And then I also have to install Julia as well. I'll post stuff about what you need to install for different platforms. If you want to, those of you who've used Python, how many of you have used Jupyter? Okay. You can also actually configure Jupyter to use Julia. And if you want to do it that way, you can do that as well. If you want to just simply edit your code in whatever your favorite text editor is, and then just simply run the Julia from the command line, you can do that as well. Right? All of those work. If you use it with your favorite text editor, there may actually be Julia bindings for recognizing the kind of code and also keystrokes and things like that. So I use one on a Mac called BBEdit. It's free. There are some bindings that you can download that actually let it recognize and appropriately stylize that code. If you're using Emacs, I'm sure there are ones for Emacs, and there's probably ones for many others. Yeah?
Any idea how well it works with Visual Studio Code?
I don't. I mean, Visual Studio in theory is meant to be flexible to allow you to work with different languages.
Yeah.
Usually you have to add some sort of configuration file that lets it know about that language. I just haven't looked to see if there's one for Julia. Okay. Great question though. And if you find the answer, please let everybody else know.
Yeah.
All right, so let's just start with, once you downloaded Julia and you run it, this is what it looks like if you're running it from a terminal or on a Mac. If you run the standalone executable, it will open up in a terminal window. Julia is, like I said, it's interpreted, but it's really, or it looks interpreted. It has a read eval print loop, but under the hood, it's actually compiling and caching these kinds of things. So just playing around with from the REPL, like Racket, because of its sort of interpreted nature, at least at this level, if you type in a value, it returns that value. Okay, so it has numeric literals, string literals. Its set of types are different than Racket's. It's all, let's see. Well, I'll show you more as we get into it. So you can interact with it here. Rather than live coding a lot of these examples, since there's a lot of ground I want to cover with this, I want to show you, I'm actually just going to bring up a file that has some Julia examples, and we'll work from there. So this is the Atom plus Juno IDE that I like to use. Again, there are multiple different ways depending on your preferences that you can work with it. So let's start with simple things. Remember there's literals, and again, there's different kinds of numeric literals. Assignment is just x equals this. So you'll notice up until where I showed you the set exclamation point, we didn't even use assignment at all when we were working with Racket, a functional programming language. That's very common for functional programming languages. Racket and all other functional programming languages try to avoid assignment, or in other words, state modification, like the plague. We're going to come back and talk about that when we actually talk about building that kind of stuff into our interpreter, and we'll talk about strengths and weaknesses of things. But Julia doesn't do that. So like, it's going to work a lot like Python again, if you're already familiar with that, and even a lot like other languages that you may have used, if not. So I can do assignment like this. IO print line will just simply print that on its own line. It does have kind of a cool, so it uses infix notation, right? Yay, no more little parenthesized expressions, unless you want to. So there's an alternate syntax. I can use plus as an infix notation here if I want 2 parameters. I can also use plus paren, comma separated list of parameters, close paren. So you notice this is calling plus the same way you call any function in Python, Java, C, C++, and so on. Right? Just function name, paren, comma separated list of parameters, close paren. So even for the infix operators, you can actually use them with a consistent call it style if you want to, and with variable arity. Questions on that? Okay. It has tuples as a data type. A tuple, actually tell you what, I'm going to go ahead and run this. It's producing a lot of output, and I'll try to sort of correlate between output here. So this is its first output. This is the second output here. A tuple, how many of you have ever worked with tuples in Python? They are, it's just simply, think of it as a small aggregate structure that stores some fixed number of things. They can be of any type. They are also, in most languages that use tuples, they're actually what are called immutable. We're going to get into mutable and immutable as we get through. But just terminology. Mutable means you can change something in place. You can mutate it, as it's sometimes called. Or immutable means it cannot be assigned to or modified. Now, tuples allow you to basically, they're sort of like mini little arrays, if you will. Sort of a hybrid between kind of arrays and structs. So you can use tuples here, but you can also use what's called multiple assignment. So with multiple assignment, it's actually under the hood using tuples. Anytime you have a comma separated thing like this, it's really making a tuple and assigning to a tuple over here. But what it effectively is doing is U gets 2 and V gets 3 kind of in parallel. It evaluates this side, assigns them here. So this multiple assignment is actually really nice because you can actually write functions that return multiple values. And you can use multiple assignment to capture the results of what's returned back. Does that make sense? So I can write a function that returns a date and a time, and then I could say day comma time equals the result of that function. Under the hood, it's really packaging up as a tuple and returning one thing, but it looks like multiple things. Python does the same kind of trick under the hood. It has its own lists. Lists, though, are just simply, there's no keyword list that you need to do, just simply square bracket, comma separated set of lists, or elements of the list, closing square bracket. This is the same as list initialization that you'd use in Python. One really, really big difference. Arrays in Julia are indexed by 1. Okay? The first element of an array has index 1. This is how mathematicians have been doing it long, long before computers were ever invented. It's programmers who start counting things by 0 because it's 0 offset from the base, right? So indexing arrays with a 0 base is just simply pure convenience for a programmer. The first thing is 0 off of the starting address. Mathematicians tend to start counting things from 1. And by the way, the only buildings I've ever seen that have a 0th floor are CS buildings. And I've been to some. So it does use 1. It's gonna be, just keep that in mind. It's something that's gonna probably come up and bite a couple of times. So I can index into elements by just simply saying the array, and index with square brackets, just like you're used to with most languages. Lists are mutable, so I can actually assign to different elements of the list. So I can access an element, I can assign to it. How many of you have ever used slice notation in Python? Okay. So Julia has its own slice notation. In my opinion, it actually is slice notation the way it should work, not the way Python does it. So this one, so if I say A2:3, this is the subarray or slice, starting at the second up to and including the third. Python does not have the and including part, which always causes me bugs. Right? So this is from 2 through 3. Now, in Python, if you ever wanted to indicate the start or the end, you just simply leave off something before or after the colon. Julia is a little bit different. It has a keyword start and a keyword end. So I would say from start colon some element of the array, or in this case, 3:end gives me the list from 3 up to and including the end. Make sense? It has push and pop operators. So let me just show you over here in terms of the output. Here's the list, here's getting the first element, here's the list after you modify the first element to be 42. Here's the slice, second 2 through 3, here's 3 through the end. Here's after you, this one is after you push on 99, so it pushes it on actually at the end. When I pop, it returns the last value, and then it's a destructive pop. So there's the last value returned, and then there's the array afterwards. So you can use this for stack operations. It also has vectorized operations. Now it's a little bit different than Python. It actually used to be just like Python, but that's one of those backwards compatible things that they decided to change. So if I write a dot plus 2, this is in essence add 2 to every element of the array A. So in Python you'd write just a plus 2. Here would be a dot plus 2, so just a small difference. The nice thing is you can actually use this dot operator notation for just about any function. It has, and by the way, I'm going to go through this quickly, so jump in if you have questions. It has something called list comprehension. How many of you have ever seen that in a language before? Okay, it's kind of a nice feature. You know how in probably CS, well, I know CS 236 you would have seen it, probably in other classes as well. You can say this set is the set of all things that are elements of this other set that satisfy some test. Right? You can basically do, or it's this set of values where this is written in terms of something like this. So I could write the same way I might write A equals the set of all values x squared, where x is an element of some list, some set B. You can write the same kind of thing, but it's just using lists instead of set. So, sorry, this example is just 2x. So this is, sorry, just to be consistent with the code, the code example. So this is, B is the list of all values to x, where x is an element of the list A. And so the way you write it is B equals x times 2 for x in A. So you notice it basically just works like a map. It's like mapping the times 2 function onto the list A, but you don't have to make a multiply by 2 function and map it on. You don't have to write some anonymous function or anything. You just write, it's the list of all x times 2 for x in A. You can also add a test to it. C is the list of all x times 2 for x in A if x is greater than 3. This would be the equivalent of saying the set of all 2x where, in this case C, the set of all 2x where x is an element of A and x is greater than 3. It's that same kind of an idea. In this case, it works like a filter and then a map. So you're basically saying for all the elements for all x in list A, if x is greater than 3, add x times 2 into the list. You're actually going to see this in a few other languages that we're going to be hitting. Questions on that? It also has dictionaries. Dictionaries are an associative array, kind of a lookup structure. For those of you who use Python, how many of you use dictionaries in Python or any other language? Okay, so a dictionary is just, think of it like a hash, if you will. So instead of I have to index the 3rd item or I've got to index something by name, I can just simply add a set of key value pairs to the dictionary. So here I can say D is a dictionary where the string Wesley maps to 3, the string Buttercup maps to 42, the string Inigo maps to 99. Guess where I got the names from. And then I can do things like, so if I print this, you actually see this dictionary printed here. If I print, what is the type of D? It's a type dictionary. Okay? And in fact, it's telling you here on this line, it's a dictionary that maps strings to 64-bit integers. I can now access this. The syntax is just like accessing an array, but it's by some arbitrary key. So here if I print the Buttercup element of this dictionary D, I get 42. You can also say get all the keys in a dictionary, gives me Wesley, Buttercup, Inigo. If I print all the values, it gives me the 342.99. Okay, so I can get all the keys or I can get all the values. I can also look up to see, does this dictionary have this following key defined? So if I said has key, this dictionary Inigo, it says yes, okay, I know about that one. If I say, does it have the key Dread Pirate Roberts, it says no. And then good work, I'll probably kill you in the morning. Okay? So we're going to use this later when we do things like storing, does this variable have this value? But so if you think of storing a variable has a value, a dictionary is a good way to do it, but you might want to know if a particular variable has been defined. So we'll use has key for that. So moving along, it's got functions. Functions are written with the keyword function. So the keyword function, the name of the function, paren, list of the formal parameters, close paren, then a body expression to return. So you'll notice that in this sense, it looks a lot like Lisp or Racket or functional programming languages. I don't have to actually put a return keyword here. Whatever the expression is, will be returned. So, sorry, whatever the last expression or statement is, whatever that returns, that's the return value of the function. It does have a keyword return that you can use. I could put it here, but it's kind of redundant. It's mainly used if you want to return and break out of the middle of some function, other than at the very end. And so the way you call them is just like what you're used to in C, C++, Java. Function name, paren, actual parameters, close paren. And again, you can take even infix operators and use this notation if you wish to. Now, for really, really short functions, it's useful sometimes to avoid all the extra overhead. I mean, here I'm saying function and n, and all I'm really writing is f of x equals x plus 1. It actually lets you write just directly g of x equals x plus, well, in this case, x plus 2. So you can actually write a quick function. This is exactly the same as if I said function g of x returns x plus 2n. You'll notice it uses end. There isn't a begin. The function is assumed to start a block that's terminated with end. If and while and other things work the same way. There's no curly braces for delimiting blocks like that. I mentioned before you can have multiple return values. All you'd say is just, in this case, return this and that, and it actually packages up as a tuple and returns it, which you could capture in a single tuple or with multiple assignment. So for example, here's a function that returns x plus 2 and x times 2, and I could say u and v equal the two outputs from calling that function with 3. So I'm going to get 5 and 6. Let's see, sorry. So if I just call it, it returns this tuple 5, 6. If I then do this assignment to these two variables and then print their sum, that's the 11. It also has all the higher order functions that you're used to from Racket. It has map, it has filter, and it has some variants of fold as well. All right, control flow. It's got if, then blocks. So conditionals, if x is less than 5, do something else if, some other test else, something end. So notice the structure is if, else if, and then as many else ifs as I want to, end. And you don't have to necessarily nest them in an if. You don't have to nest another if inside of the else part of another if. You can just say if, else if, else if, else if, else end. Okay? Notice there's never begins. Each one of these is assuming to start a block of things, which is terminated by the next else if or else or end. Loops. Let's focus on the while and I'll explain the let in a minute. This is just a while loop like you're used to. While z is greater than 0, do something, end. Okay? You'll notice inside the loop like this, you're typically modifying this counter or doing something to modify this test so it'll eventually break out. There's an issue with scoping that Julia uses. Julia, it does, so you guys have learned before that modifying global variables is bad practice, right? Hopefully that's been preached to you before. Julia actually takes that a step further. Some other languages do it. If you want to modify a global variable, you have to explicitly sort of flag that you are. So you're not allowed to arbitrarily modify a global variable without actually using a keyword global, the name of the variable. That sort of allows it now to be modifiable in your current scope. It sort of says, hey, everybody else on my programming team, I'm modifying this global thing, and I know it's bad practice, but it's really necessary here. So that's why I'm just using a let. A let is like a local definition. Just let z equal 5 in this block, and then so it has something it can modify. Everything we're going to write is inside of functions or other things, and you won't run into that. I just had to do it for this example. It's got for loops. But it's like Python for loops in the sense that it's for x in. So rather than sort of having an initializer and then a test and an incrementer and so on, it's for x in some list A. And this can also be created through other different kinds of means. So for x in A, it's going to print them out. It can also do a for loop for all key value pairs in a dictionary. So it's got a number of different for loops over different kinds of data structures. It has try-catch blocks that are used to what you've seen in Python, but in other languages as well. Try this expression, and if something bad happens, an exception is raised, catch it, and then do something with it. Let's use our remaining time to talk a little bit about types. It has a type of operator, which is useful for finding out what the type of a variable is. So you notice I'm never declaring what the types of my variables are. It doesn't have what's called manifest typing. It's just doing it dynamically. But I can always ask what the type of something is. We'll use that a couple of times in the lab. You'll notice when I declared functions earlier, I didn't say what is the type of the parameter x. I can actually pass it anything. However, if you want to, you can create typed functions by just simply putting the syntax for specifying that a particular variable is a particular type is the variable name : the type. So this is a function h that works on inputs that are integers. Now, you've all seen overloaded functions before, right? If I want to, I can actually create another version of h that works on strings, another version of h that works on some other type, and it will automatically call the right one. Also, if it doesn't find one that's an exact match, it will try to find one that it can type promote. So int is actually a sort of a subtype, if you will. This subtyping is important in Julia. We may have to pick it up next time as well. Int is a subtype of number. So if I wrote a function that worked on any number, sorry, actually it's a subtype of, say, real number, and real number is a subtype of number in general. So if I had something defined for a real number, I could pass it an int, and it's going to go ahead and match it. It'll type promote it. So again, I can do it for different kinds here, and it'll dispatch to the right one. Last little bit. It has an aggregate type called struct. It's a lot like the structs that you used to in C++. Although in C++, how often have you used structs? It's probably using classes far more often, right? So I can say struct, so struct, and then my point, and then I give it fields. Now I can choose to put types on the fields, or if I leave them off, I can put anything in there. Okay? Now one of the things about this is, if I leave it off, it's not that those fields don't have any type. It's that they do have an assigned type. And remember I talked about sort of there's this type hierarchy. Number, int is a part of a real number, or subtype of real number is a type of number is a type of something else. Sitting at the top of that hierarchy over all the other types is a type called any. So if you want to, you can actually declare that a particular variable is of type any, in which case you can now put anything into it. Does that make sense? If you leave off the specifiers,